So today we introduce a method called impulse and momentum of looking at the motion of particles. Now, like the method we just finished looking at, work and energy, impulse and momentum, the derivation of the equation begins with the equations of motion. Sum of the forces equals mass times acceleration. But by manipulating that equation, we come up with the one that's shown here. The quantity m times v, by definition, is called momentum. And you can see that the change in momentum is going to be dictated by this term in the middle. And we call the integral of a force over time the impulse of a force. Of course, the units of this, as you can see, are going to be force times time. So in the SI system, Newton times seconds. In the US system, pounds times seconds will be the units of both impulse and momentum. Now, like the equations of motion, we have the vector equation, sum of the forces equals mass times acceleration. We broke that down into scalar equations depending on what components we were looking at. And so a lot of the problems we're going to be looking at least initially, are going to be one-dimensional problems. So in the x direction, for example, we can say that the mass times the velocity in the x direction, in other words, the momentum in the x direction, plus the summation of the forces integrated over time, but only the forces in the x direction will impact the final momentum. And again, if you can have similar equations for y and z if need be. Now, comparing the methods, work and energy relates forces and velocities to displacements. Notice time's not involved in the work-energy method. With impulse momentum, forces and velocities and time are related, so displacements are not included. So it depends on what you're given and what you're trying to find as to which one of these methods that you want to use. But in all cases, you can use equations of motion. But usually, if you don't need to find everything, then one of those other, either work and energy or impulse momentum, tend to be a little simpler, because in equations of motion you are finding accelerations as an intermediate step and then relating those accelerations to velocities, displacements, and the time. So both the work and energy and impulse momentum can be considered shortcut methods where you don't need all the information that you get out of the equations of motion. So here's an example. This crate is sliding down a ramp. It hits the floor at point A at a given speed and slides with friction and comes to a stop at point B. And we can see some of the parameters there. 20 kilograms is the mass. Coefficient of friction is 0.3. And so we're asked to find the stopping distance, and we can use work and energy for that. But if we want to find the stopping time, we can use impulse momentum for that. And of course, we can use equations of motion to find both of those things. So we draw a free body diagram first. It's relatively trivial here. All we really need to know is to find what is the friction force, which in this case is just 0.3 times the weight. And note, though, that if we define the direction of motion as the positive direction, in other words, positive x is going to be to the left, then the friction force acts in the opposite direction of that. So whether we're using work and energy or impulse momentum, because of the fact that the friction force is opposite the direction of motion, it's going to be either a negative work done or a negative impulse. So we start out with our initial momentum, just the mass times the speed. The final momentum, again in the x direction, is going to be 0. And relating those two are the force integrated over time. Again, the only force we have in the x direction is friction, which is 0.3 mg. It's in the negative x direction, so hence the negative sign. And integrated over time is just because the force is constant, it's just going to be the force times the time. And using that, plugging into our equation here, we can easily solve for time and find that it takes 3.4 seconds for that box to come to a stop. But notice what we didn't find out of this was the stopping distance. If we use work and energy, and won't go through all the details since we've done that a lot, but notice the only force doing work is the friction force. Again, it's going to be doing negative work because it is in the opposite direction of motion, and we find that the distance is 17 meters. With the equations of motion, you start with the sum of the forces in the x direction, and from that calculate the acceleration, which is negative in this case because it is slowing down, and then find both the stopping time and the distance, which agree with our other methods. Now, toward the end of the class, we talked just a little bit about multiple particles, which we'll get into in the next class as well. When you have more than one particle, we're looking at the summation of the momentum being affected by the impulses of the external forces acting on that system of particles. And there will be cases such as impacts where there are no external forces. In those cases, we say that momentum is conserved. So that'll be next class. We'll do a few more impulse and momentum problems, especially those with multiple particles. And we'll begin looking at impacts between two particles, which will extend another class beyond that as well.